I need to talk about what NVIDIA showed off in Taipei because I have not stopped thinking about it since. On May 31st, Jensen Huang walked out in front of more than 30,000 people at GTC Taipei right before Computex and announced a computer that puts data center hardware on a desk. Not in a rack, on a desk, next to your coffee. It's called DGX Station, and the number everybody latched onto is 748 gigabytes of coherent memory. 748. If you've ever tried running a decent open model at home and watched your graphics card choke because it only has like 24 gigs of VRAM, that number should feel almost personally insulting. I'll break down what's inside, what it really does, where NVIDIA is stretching things, and whether it matters if you aren't a Fortune 500 company. And I'll tell you which of these boxes I'd actually buy, because it isn't the one you'd expect. Quick thing first, if you like hardware breakdowns where somebody reads the spec sheets instead of reciting the press release back to you, hit subscribe. I've got a whole run of local AI hardware videos coming. Okay, silicon. Now, the heart of the DGX Station is the GB300 Grace Blackwell Ultra Desktop Superchip. Yes, that's the real name. NVIDIA has never met a superlative it didn't like. Here's what it is: a 72-core Grace CPU on ARM Neoverse V2 cores and a Blackwell Ultra GPU carrying 20,480 CUDA cores. Those two aren't sitting on a motherboard politely chatting over PCIe. They're fused with NVLink C2C, a chip-to-chip link running at 900 gigabytes per second, bidirectional. PCIe Gen 5 gives you around 64 gigabytes, so the pipe between processor and GPU is roughly 14 times wider than one on your desktop. Memory cores in two pools. The GPU side carries 252 gigabytes of HBM3E at 7.1 terabytes per second, which is, well, frankly, absurd. The Grace side brings 496 gigabytes of LPDDR5X at 396 gigabytes per second. Add them up, and you land at 748. But the capacity isn't the story, coherence is. Both pools live in one unified address space, and either processor can address the whole thing directly. No explicit copying, no shuffling tensors across a bus while you watch GPU utilization flatline. On a traditional multi-GPU rig, moving data around is a real engineering problem that eats weeks of somebody's life. Here, it just isn't a problem. That's the actual innovation, and it keeps getting buried under the petaflop marketing. Speaking of which, up to 20 petaflops of AI compute. That's FP4 with sparsity. Hold on to that asterisk. You also get a ConnectX-8 Super NIC pushing 800 gigabits per second, 3 PCIe Gen 5 slots, and multi-instance GPU support, which slices the GPU into as many as 7 isolated instances. So a small team can share one box. And one detail NVIDIA does not put on the side: the base system has no video output. The GB300 is a compute-only part. Want a monitor? Add a separate GPU, which is both hilarious and very telling. Now, if you run LM Studio or Ollama, you know the wall. You find a model you love, check the file size, and do the sad little arithmetic in your head. A 70 billion parameter model in full BF16 needs roughly 140 gigabytes just for the weight, before a single token of KV cache. Your 4090 has 24 gigs, your 5090 has 32, so you quantize. You crush it to 4-bit, accept a dumber, weirder model, and tell yourself it's fine. Or you rent a cloud GPU and your data walks out of the building. The DGX Station deletes the entire decision tree. A full precision 70B loads with enormous headroom left, room for a massive KV cache, a long context window, a second model running alongside it, your vector database, your retrieval pipeline, all of it. You stop optimizing around a ceiling and just work. It goes further than that though. Llama 3.1405B in full BF16 wants around 810 gigabytes. Still over the line, but with optimization, it's in the conversation, which was impossible on a desk a year ago. For anyone in healthcare, law, defense, or finance, this isn't nice to have. Data sovereignty is the whole ballgame. Prompts, context, outputs, all of it stays inside your walls. NVIDIA says early customers include Snowflake, EPRI, and Microsoft Research, and that mix tells you exactly who this was built for. Now, let's be adults about the marketing. NVIDIA says that the DGX Station runs models up to 1 trillion parameters locally. Technically true, practically read the fine print. A trillion parameters at 4-bit is roughly 500 gigabytes of weight. That fits inside 748. At 8-bit, you're pushing a terabyte and you're out. At 16-bit, you aren't even close. So the trillion parameter headline is a 4-bit headline. Full stop. But to their credit, NVIDIA did real engineering here. Their NVFP4 format claims near FP8 accuracy, with differences often under 1%, while cutting the memory footprint 1.8 times versus FP8 and 3.5 times versus FP16. If that holds up outside the lab, it's a serious achievement, but near FP8 is not FP16, and anybody who has watched a quantized model start looping halfway through our reasoning chain knows that the gap is real. My read, the trillion parameter number is the demo. The full precision 70B and 120B numbers are the product, and those are excellent. Same with compute. 20 petaflops is a huge amount of throughput, but it's FP4 with sparsity, the friendliest yardstick available. Dense workloads land lower. That's not lying, that's how every chip company has quoted numbers since forever. Here's where it gets spicy though. NVIDIA isn't selling a Founders Edition. It ships the motherboard with the CPU and GPU already fused, and partners like Asus, Dell, Gigabyte, HP, MSI, and Supermicro build the workstation around it. NVIDIA never announced an official price, but an MSI expert station WS300 showed up on CDW in late February at $96,995.99. $97,000. Across configurations, expect $85,000 to $115,000. So no, this is not a hobbyist machine, and anyone telling you to start saving for one isn't being straight with you. But compared to what it replaces, a previous generation DGX Station ran around $150,000, and if you rent instead, an 8-way H100 instance on AWS was listed at $98 an hour, and even after price cuts, sits nearly $55 on demand. Run that across the clock, and you burn through the cost of a DGX Station in 2 to 3 months. That's the pitch. If your team actually saturates a GPU, the box pays for itself faster than people assume, then keeps paying quietly on your power bill instead of your cloud bill. Your data never leaves the office, and in a regulated industry, that alone can justify it. One caveat to be fair, the Grace CPU is not competing with a modern Xeon or EPYC on raw throughput. Grace exists to feed the GPU and not to be general purpose monster. If your pipeline leans hard on the CPU, you'll definitely feel it. Now, if all this is a little bit too much for you, and who can blame you, NVIDIA's answer is the DGX Spark. 128 gigabytes of unified memory, 1 petaflop of FP4, the GB10 Superchip sitting at $4,699 after a memory-driven price bump this year. It handles models up to roughly 200 billion parameters, fine-tunes up to 70B, and ships with Llama pre-installed with a full CUDA stack. Link to over ConnectX, and you've already got 256 gigabytes. It is not fast, that's for sure. Bandwidth sits around 273 gigabytes per second, so a 70B at Q4 crawls out of a couple of tokens per second. Anyone selling it as a speed demon is lying. But speed isn't the point, it's a development box that never tells you no. The obvious comparison is Apple. Mac Studio is the default answer in every local AI thread online, and the M5 Ultra should reach 256 gigabytes at around 1200 gigabytes per second. On paper, more bandwidth than Spark by a mile, but it slipped to Q4, the big memory configs quietly vanished from Apple Store, and the software gap is real. VLLM only landed on Metal in early 2026, and it's text only. Tensor RT-LLM doesn't exist on Mac, and if CUDA tooling matters to your work, that settles it. Then there's the RTX Spark, and this one I am actually excited about. Announced at Computex alongside the DGX Station, it's an ARM-based Windows Superchip built with MediaTek, so 20 Grace cores, 6,144 CUDA cores, up to 128 gigabytes of unified memory, 1 petaflop of FP4 in a laptop weighing about 3 pounds, which weighs less than my laptop that I'm doing this video on. Morgan Stanley's channel checks put flagship and 1X systems near $2,899. Run the per gigabyte math, and that's cheaper memory than the Spark it's named after. Now, here's what I think is really going on. The DGX Station isn't a product for most of us, it's a proof. Jensen said every future NVIDIA architecture generation will ship a desktop, a laptop, and a workstation, and call this the first real reinvention of the PC in 40 years. Windows support arrives in Q4, built with Microsoft and running an agentic runtime called OpenShell that sandboxes agents and containers. Now, am I skeptical Windows on ARM nails it first try? Absolutely. Everyone who walked that road limped away, but NVIDIA shows up with CUDA, 30 years of GPU software, and the whole PC industry behind it. That's a very different starting position, and I love where this is going. The last 3 years of local AI have been one long exercise in compromise. Quantize this, offload that, accept a dumber model, or hand your data to somebody else's server and hope. The DGX Station is the first machine that says you don't have to pick. It's expensive, the trillion parameter claim is pure marketing, the CPU isn't a beast, fine. Compromises, sure, but not as big as previous compromises. But the direction, for once, is right, and direction trickles down. Today, it's $100,000 on a desk. That's the actual story. Not the price tag, not the performance, the trajectory. Now, if you've got something out of this, drop a like. It takes a second, and it's the main reason these videos reach new people. And subscribe for the follow-up, because I'm getting hands-on with the Spark tier hardware next to see what these things really do once the marketing slides are gone. See you in the next one.